Welcome back to our series on the road to AGI. In today's episode, we're going to be taking a deeper look at the next revolutionary moment in AI. Before we get into today's video, if you stick around to the end, you'll learn how to get access to our new free mini AI ChatGPT prompting course before anyone else. The first generation of AI systems were nowhere near as powerful as the ones we know today, but each step throughout the development process has been vital to get to where we are today. For one, they were slower. It took long stretches of time to come up with simple answers, and they were still prone to a lot of mistakes. This was the case with the first generation expert systems. However, after the AI winter of the 1970s, the second generation expert systems blew the first generation, such as Dendral and MySyn, out of the water. But while the second generation were clearly better, they fell far short of the goal. At this point, for AI to move to the next level, a next level discovery was required, and something better than the rules-based algorithms. To do so, researchers had to go back to a method that was largely considered ineffective: machine learning. But to get to this point, let's take a journey back in time. Research in machine learning is as old as research in artificial intelligence itself. Looking back in history, it all started in 1943, when Walter Pitts and Warren McCulloch presented the first mathematical model of neural networks in their paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. In the paper, they showed that neural networks can be used to represent and process information, and they also showed that neural networks can be used to model the behavior of biological neural networks. This seminal work by Pitts and McCulloch laid the foundation for what we know today as machine learning. The initial milestone by Pitts and McCulloch was followed by Donald Hebb in 1949. Hebb published a book, The Organization of Behavior, where he laid the groundwork for the relationship between neural networks and brain activity, which eventually became a monumental pillar in the development of machine learning. However, the first real work on machine learning would eventually come in 1952, when Arthur Samuel wrote the first ever machine learning program, his game of checkers. The program was a progressively intelligent program that played checkers, but the kicker was that this super smart program could continuously fine-tune its strategy by learning from winning moves. At this time, AI was enjoying the first boom, so machine learning research also blossomed with several high points. First off, in 1957, Frank Rosenblatt designed the perceptron, which was the first neural network for computers that simulated the thought processes of the human brain. After this, in 1966, Ross Quentin introduced the ID3 algorithm, an early decision tree learning method that popularized the decision tree method. The decision tree was simple, but had tremendous potential, because with it, programmers had a simple interpretable model to create programs that relied on data-driven decision-making. What followed was the nearest neighbor algorithm in 1967 that launched computers into a whole new world of basic pattern recognition. The nearest neighbor algorithm was used to map a route for traveling salesmen, to map their route and ensure they visit all cities during a short tour. Despite all this eye-popping progress, everything stalled when the AI winter of the 1970s hit. Interestingly, there was some pessimism that machine learning was less effective, so almost nothing happened during this time to further machine learning except just a few sparks that kept what was left of the fire going, such as the invention of the Stanford cart. In 1979, a group of students at Stanford University developed a robot known as the Stanford cart. This bot relied heavily on machine learning programs to continually develop the intelligence that enables it to navigate obstacles in a room. Now, the Stanford cart came at the brink of the next AI summer, which saw funds flow into AI research and an increase in interest in AI development. So life restarted for research in machine learning with the rediscovery of the concept of backpropagation. This was largely due to the success of a paper published by David Rumelhart, Geoffrey Hinton, and Ronald Williams in 1982, Learning Internal Representations by Error Propagation. Another jolt of electricity that jump-started the heart of research in machine learning was when Gerald de Jong introduced explanation-based learning, or EBL. This basically allowed a computer to analyze training data, create its own general rule, and follow it by discarding unimportant data. Meanwhile, artificial intelligence was running on the second-generation expert systems, which were fundamentally better than the first generation, but nowhere near the capacity of machine learning-driven systems. The rule-based systems had some serious limitations. First off, they were not very flexible and could not really adapt to new situations. Beyond that, these systems needed a lot of expert knowledge to build and maintain. So, to overcome these failures of the rule-based system, there was a big shift. A shift to machine learning systems, meaning that instead of algorithms being limited to rules in the past, they can learn from data without being explicitly programmed. leading to more flexible and adaptable systems. However, there were several factors that made this major shift from rules-based system to machine learning possible. Top of the list was the availability of large datasets. Machine learning algorithms were largely dependent on data. The algorithms needed data to learn from and develop its capabilities. So with the availability of large datasets, it became possible to train machine learning models much more powerful than rule-based systems. A beacon for this era was IBM's Deep Blue, a chess-playing expert system that ran on a special purpose-built IBM supercomputer. After several trials, IBM's Deep Blue chess system became the rave of the AI world when it became the first computer to win a chess match. In 1996, Deep Blue lost woefully to Garry Kasparov, the reigning world chess champion at the time. In a match of 6, the system lost 4 and won just 2. However, after some upgrades and tweaks to the system, it defeated Kasparov in a 6-game match, winning 2, losing 1, and drawing 3. This feat was possible because of the availability of vast amounts of player data that was used to train the system. The ability of Deep Blue to also learn and self-improve was key to defeating Kasparov in the 6-match game. This feat was indeed a new herald in the development of artificial intelligence. But do you think Deep Blue stands a chance against modern chess software? Let us know your thoughts in the comments section down below. Now that said, let's move on to the next reason that made the shift towards machine learning possible. So, on the other hand, the development of faster computers also played a vital role in the shift to machine learning. Machine learning algorithms can be computationally expensive to train, so faster computers made it possible to train machine learning models more quickly. However, one event that changed artificial intelligence and the application of machine learning permanently was the decision to merge several government-owned networks of computers to form an interconnected web of networks, known as the Internet. So how did the rise of the Internet impact the emergence of machine learning? Hang in there as we go through the web of changes and improvements that the Internet brought to machine learning. One of the most influential developments in the rise of the Internet that transformed the landscape of machine learning was the development of those tiny chips known as integrated circuits or microchips. But what really makes this development a game changer? You see, in the past, machine learning was limited to big corporations with high computing power. These guys held a sort of monopoly because they had supercomputers that could generate vast amounts of data needed for machine learning. However, this ended with the advent of the microchip, which not only shrunk the size, but also the cost of generating vast amounts of data for machine learning. So because of the microchip revolution that accompanied the Internet, everything from phones to computers and other appliances use these chips, and they generate vast amounts of data needed to train machine learning algorithms. Remember, machine learning heavily relies on data. Now, beyond data gathering, as the Internet grew, so did the application of machine learning. In fact, it exploded. For example, in the 1990s, searching for relevant information on the Internet, which at that time had a vast amount of information, was a very tough job. It was a bit like searching for a needle in a haystack. You had to know the address to the specific site you were searching for to access it. So how did machine learning change all that? It all started with the earliest examples like Archie, then the likes of WebCrawler, Alta Vista, and Lycos. With these search engines, you could search for information from the vast Internet database. Now let me put this in perspective so we can understand how much of a breakthrough this was. Prior to these search engines, you had to know the exact name of the website you were looking for. Without that, you had no chance locating it. However, with search engines, all you need is at least a keyword of the website. That's like going from 0 to 1000, but this was nothing compared to what followed it. In 1996, Google developed a game-changing algorithm, the PageRank algorithm. And here's the thing, instead of just relying on keywords to complete a search, the PageRank arranged web pages in terms of relevance by considering the quality of links pointing to it. And with this approach, search results were more accurate than ever. Now, machine learning algorithms are key to the more personalized internet experience we have. For one, if you check your YouTube homepage, you will get a clearer picture. The software recommends video based on your search history, clicks, and it even studies your engagement pattern and other activities on YouTube. So your videos are personalized, tailored just for you, because the algorithm learns from your past behavior to recommend what you may like. This highly personalized recommendation is not limited to just YouTube. Almost every internet platform applies this machine learning approach. But this just scratches the surface of how much machine learning affects our internet experience. Because as much as machine learning is at a higher level, there's something higher, or would I say deeper. In the next episode, we will go beyond machine learning to uncover the deeper parts of AI that will blow your mind. Until then, make sure you're subscribed to Tectonic Shift for more AI content and turn on the notification bell to keep up to date with the coming episodes. And if you enjoyed the video, don't forget to hit the like button If you made it to the end, we're about to launch a new newsletter. The weekly newsletter will cover all the new and exciting things happening in AI and highlight the latest tools and plugins we hear about. As a major bonus, those who sign up today before we launch will get a 5-part mini AI chatbot prompting course. We've been using AI since before it came out and have learnt through trial and error the most effective ways to prompt. By using our methods and secrets, you can become 32 times more effective at prompting and getting the result you want. Check out the link in the description. See you in the next one.